Hey everybody, it's Norm from Tested.
And it's Jeremy from Tested.
Welcome to Projections, our show about AR and VR. Now, Jeremy, one of the technologies that makes the modern take on VR possible is very precise and high frequency positional tracking.
That's right, yeah, that's something that we didn't have at all with the first Oculus developer kit. And then once we finally experienced positional tracking with the head, it became a whole new world of immersion, didn't it?
It's right. It's how the computer system and the engines know where you are and where other objects are, whether it's your hands or things you're holding in the real world, in the spatial environment.
Right.
And everyone does it differently.
Well, with the Oculus Rift, we've got these IR, basically cameras that read the little tiny LEDs on your track controllers in your headset. And on the Vive, it's sort of the reverse, right? We have laser projectors, these lighthouses that we put it in the corners of our room, and they emit or IR lasers that the headset and the controllers actually detect. But it's all outside in. The dream is to do the reverse, right? Inside out.
Purely inside out.
Because currently, the downside of outside in is that we have tracking volumes.
Yeah.
We have spaces within which we are perfectly well tracked, but if we go outside of those, dead zone.
Right, and I guess you could say the Vive system, the SeamVR system, it's technically an inside-out solution, but the volumes are still limited.
Right.
I mean, like the Vive controllers, these are the camera sensors essentially looking at the lasers from the beacons, but you need the beacons, you need the point of reference, and a purely mobile, tetherless inside-out tracking solution would need nothing but the cameras on the headset or even the controllers. And we've been brought to believe that inside out is a tough problem to solve.
I'm sure it is.
Yeah, and there are many smart computer scientists working on the problem. I know at Oculus they showed us the Santa Cruz VR prototype, which is an inside-out tracking prototype, wireless headset based on their mobile version of the Oculus platform. But the demo that we got last year for that, it was a very controlled environment. We didn't know how much pre-scanning had been done to the room, whether the high contrast and the colors in the room, the lighting, like what are the variables that can affect inside-out tracking.
Right, and you didn't even know if that's going to become a product or what it is. It seemed to have an embedded computer, so it wasn't connected to a large, PC or anything.
Yeah, but one of the benefits of the Dream inside-out tracking solution is that it would be wireless and you could basically walk around anywhere.
Right. I mean, isn't that kind of what HoloLens is doing on the AR front? They do live real-time scanning of the environment in front of you, but the problem is that costs $2,000?
Yeah, it's pretty expensive, and Meta does the same thing, where it does some scanning. It's a sensor fusion system. They're using a bunch of sensors, including the IMU and cameras looking at the world to measure where you are.
Right.
And one company that's experimenting with inside-out tracking is actually a company called Occipital. They make a depth sensing camera.
You've been using their iPad attached camera for years now to do 3D scans of things.
Yeah, this is called the structure sensor. It has been out for a while. And yes, we can use it to scan people, to make little 3D prints of people. And there is an application that they have for this to scan rooms, to have a 3D model of your home environment, for example.
Right.
But they've modified this structure sensor to work for AR.
Right, so they have taken the exact same sensor and attached it to a headset, which is basically like a Gear VR or something that you would put your phone into, that turns it into an inside-out tracked AR headset.
Right, and what's interesting about this, they call it the Bridge headset, is that they use the depth sensor on their structure sensor. It's basically an IR blaster and camera, and wide-angle camera, to pre-map a room. So I'm using the sensor, basically mapping out my living room space, then putting on the headset, and then passing through your phone camera a superimposed video image projected on top of the 3D model.
Right, now we got a chance to try this, and I gotta say, there was some new stuff involved here. Seeing a augmented reality, which on a robot, for instance, moving around the space, avoiding obstacles that had been mapped in VR, like a little chair that was in the center of the room or a table. It could actually do pathfinding around these 3D objects in the space and be occluded by them if I brought my head down. That's pretty neat stuff.
Yeah.
there was also the ability to do sort of a chaperone system where if you walk up towards one of the objects, it fades, it becomes brighter, so that the actual geometry of the thing, rather than just the border of your play space, the actual geometry of the objects could fade into view. If, for instance, like you change your environment to a virtual reality environment, where it's just completely, fake stuff. But if you move towards something that you're about to stumble over, they'll indicate that by fading the geometry up in front of you, which is kind of neat.
And that's the key, adding geometry data, mesh data, to the live pass-through image. Because you can do live pass-through image with a wide-angle camera. You can do it on the Vive right now, pass-through, but that's just flat imagery. There's no actual geometry data. But you still have to pre-scan it with this bridge system. It doesn't do real-time updating of meshes.
Right, like the HoloLens might.
Exactly. So that experience, it's out for developers now. You can buy the kit with this pass-through system and the structure sensor, about $400, but it's not a consumer product. It's not a mainstream product. I think it's for developers to really learn in AR in a cost-effective way without spending a couple $1,000s on an AR system, and kind of develop UI and UX lessons in AR.
I would say it's probably a good developer kit too. I mean, it's not consumer ready.
No.
I wouldn't recommend it for consumers. There's certainly a latency factor. The frame rate is nowhere near what you would want from a solid consumer product. But it is interesting to see these baby steps into augmented reality, developed by people and put out into developers' hands.
Now, the other thing that Occipital is doing is experimenting with a positional tracking system in VR, an inside-out system. They're calling this Occipital tracking, and it's using a new sensor called Occipital Core.
Right, they're calling it the next generation of their structure sensor.
Now, what's interesting about this tracking system is that it does use IR blasters and a receiver, or it can track with just one camera, not even a stereo camera, a monocular inside-out tracking system, as you would have maybe on a phone. And we chatted with the CEO of Occipital, Jeff, to learn about Occipital tracking and also get a demo. So let's jump to that.
So Occipital tracking is a new software suite, basically, that allows us to do what the market is calling inside-out positional tracking, really just figuring out where a user is located in space very accurately using cameras on board the device instead of base stations or cameras in the environment. And that's basically what Occipital tracking does, and it does so with a variety of different sensors. We can operate from all the way down to like a monocular camera with an IMU, all the way up to a system with many cameras. And at a gist, that's what Occipital tracking is, but we could dive into specific parts.
Yeah, so you've been doing inside-out tracking with your structure center for years now.
Yeah.
But this is an entirely different sensor set, right? Can you talk a little bit about what the various sensors are you have here?
Yeah, absolutely. So this right here is called a structure core. And you can think of it in a lot of ways as kind of like the next generation of the structure sensor. But unlike where the structure sensor was a prosumer, consumer accessory that you could attach to your tablet, like your iPad, structure core is kind of the guts of that system. But it's a different set of guts. It's not the same. As you pointed out, there are different cameras on here. So we have a fisheye camera, which is basically a very wide view. We have a pair of infrared cameras, which are looking at the world in the infrared spectrum. And we have a projector, which is projecting texture. It's a fixed texture pattern out onto the scene. The reason we do that, the texture projection, is because in a lot of scenes, you don't have any interesting visual features to track. So if somebody points at a white wall, there's really nothing there coming back other than just white. And so what we do is we project this texture out onto that wall, and now we've got a nice pattern that we can pick up.
Is that a laser projector?
It's laser-based, yeah. There's a laser in there. There's some other crazy optics, holographic type optics. They actually break a single laser beam into many thousands of points.
Infrared.
Infrared.
Okay. I mean, when we look at the very early days of just tracking with a computer vision system, optical system, fiducial markers were very popular. They were reliable, and that was positional tracking to an extent, but that's having a known object in the real world that's not going to be moved, that you're moving in relation to, without having those locked-in objects. How does computer vision with a single camera track and align the world?
Yeah. So yeah, you're pointing out that how do we manage to track a world from a single camera? It is one of the hardest problems. So this is the problem of simultaneous localization and mapping you may be familiar with. but you can't, if you don't have a map, like in the case of a fiducial, you have something you already know what it looks like, and so you just need to observe it and then measure where it's located. In the case of simultaneous localization and mapping, you don't have a map, and you have to simultaneously figure out what am I looking at and where am I? And it turns out if you solve those problems at the same time, it is possible to do both of those things, figure out what you're looking at and where you are, and then you start to build a map. You start to build a point cloud or a different representation of the scene. In the occipital tracking system, we build not only a point cloud, but also like what you could think of as like a line cloud, actually. We also find a bunch of lines in the environment. In a lot of man-made environments, there's a lot of lines, and so we take advantage of these. But by solving these problems simultaneously, you can build that map and track it. And then by solving other issues that happen in such a system, like drift and other problems, you can really approach a system that is able to instantly turn on, track its position, build a map all together all at once, and do away with the need for fiducials or base stations.
Before we started chatting on camera, we were talking about how the future is inside-out tracking.
Yeah.
I mean, everybody seems to agree on that, and it seems to have come online faster than anyone expected. So maybe by the next generation of VR headsets, everything's going to move towards inside-out, and we're looking forward to that. My question is, how do we handle controllers with an inside-out tracking solution, unless the controllers themselves are, smart and have their own inside-out tracking systems as well?
Yeah.
Is that what you foresee, or are we going to see an amalgamation between inside-out and outside-in for the near future?
That's a great question. So one partial answer to that is we found an interesting optimum solution where you don't have a controller tracking solution is to use a 3 degree of freedom controller. Mm-hmm. I don't think this is the long-term full solution, but it turns out that if you have your head tracked and your environment's mapped and you're able to interact in VR, you can use a 3DoF controller to point and grab and do many of the things that you do with 6DoF. So it's not a full solution, but that's one cheat, is actually just use 3DoF and make sure you know which direction's forward. You can do a lot of stuff. Now, to get to full 6DoF, so we can really start to reach in and paint and this kind of stuff, well, one solution is to actually use cameras, maybe a different set of cameras on the headset to track the controllers. And this works, the cameras that we can make today, the camera on here is about 160 degrees. You can make cameras that go even higher, like 200 degrees or more. And so now you have one camera that can see pretty much the same as the human field of vision. And so if your controller is anywhere within this range, it can be tracked. So that's one means of doing it. There are corner cases though. If you rest the controller down at your side, unless you've got weird cameras looking down here, it's kind of an unsolved problem. And so nobody really has a great solution to that. One of the ideas is what you mentioned, which is what if we put cameras on the controllers themselves? And then they can keep track even when they're in a different orientation. Right. But the short answer is, I don't think we have a clear answer to how to fix this. And there are some other interesting technologies, electromagnetic fields. So you could emit a field from the headset and you could detect where you are based on the strength of that field.
Right, so what the STEM system
like
uses.
the STEM system,
yeah. Sixth sense. When you're talking about the computer vision aspect, right, a lot of it's compute. You're finding that balance, it looks like, between how much compute you want to do and how fast you want to refresh your map of the world. Are you designing the system and just anticipating that we'll have more and more compute, more and more memory, or are you designing for something that's going to work today? And today, is it 60 hertz, 90 hertz? How fast is it refreshing?
Yeah. So our system today is capable of mapping and tracking simultaneously. So you turn it on and you go. It's updating the map at kind of a variable rate, but it's multiple times per second that it's updating it. And it's tracking frames anywhere from 30 to 60 frames per second, but it's using IMU data anywhere up to 2,000 hertz or 2,000 times per second. And all this information is fused very tightly, and so we emit poses to something like a Steam VR type system, or the Open VR system. We emit poses at 1,000 hertz. And so, and if we do our job right, if we fuse information from the IMU and the camera in an optimal way, it starts to matter less exactly what rate your camera's running at. But if you don't fuse it optimally and your IMU isn't calibrated well enough or isn't a good enough IMU, you need to track the camera faster. But anyway, generally speaking, to answer your question, we're tracking the camera anywhere from up to 60 times per second usually. And then IMU at 1,000 and updating the map multiple times per second.
That seems like a secret to SLAM and sensor fusion systems, that as long as you have a baseline, really fast refresh rate, the brain's gonna feel that it's okay. You can compensate for lower refresh rates in other parts of the system.
Yeah, I think the SLAM system, thanks to the IMU, we can get the same kind of like latencies that you can get with an outside-in system, because we can use that IMU to give us a very up-to-date information, even if the camera is coming some number of milliseconds later. So, in fact, many of the latencies that you perceive in a system like this start to be less about the perceptual system and more about the display system. Because the display system has to get information, has to time warp the scene, has to get it on the display. But fortunately, everybody is working on all these different pieces, and so 20 millisecond motion to photon latency is common these days. Maybe it'll be 5 or 10, and in the HoloLens, it's even less because they're doing crazy stuff, which they have to because you're looking through to the real world. But yeah, I mean, it's a system problem is really what it is.
I mean, there's movement refresh rate, how fast you expect a user to be moving.
Yep.
We're not moving crazy fast most of the time. There's the occlusion with the field of view. What are environments? What type of environments is the occipital tracking and structure core best suited for?
So I think in some ways we kind of probably at this point have a little chip on our shoulder, some frustration, because we build this technology that works amazing in like a consumer's living room. And then we go to show it to folks, and invariably we're in a room like this. We're in like a white table, glass wall, bright light over here, not light, dark over there. And so occipital tracking has been designed to handle really difficult environments like that, where you've got a huge variance in lighting, you've got reflective surfaces. We need to be able to ignore reflections and things that aren't supposed to be tracked. And so for that reason, our system is able to handle that kind of an environment.
So this is a PC-based solution on occipital tracking right now. What are your hopes for bringing that to mobile? Because currently your mobile solution has to pre-scan environments. This is a learning system. That's for huge RAM requirements. I'm sure the processing requirements are much higher. But with cell phone curves still rapidly increasing, do you imagine this coming to mobile as well?
Yeah, so occipital tracking actually runs today on Android as well.
Oh.
So you saw a Windows demo, but we have it running on Android. And we don't have an Android headset demo today. Hopefully next time we will. But the tech does run there. And thanks to all of our efforts in optimizing for example, the iOS platform, a lot of that work that we've done in the past for things like bridge and structure sensor is able to come over and make us be faster on these devices as well. So what's interesting is the Windows stuff that you saw, we haven't really put much time into optimizing performance, but on mobile we spend a huge amount of time because you only have a small compute box. And so you need to use things like the GPU, you need to use things like maybe the DSP, the vector processing instructions that are on those ARM processors. But they've gotten incredibly powerful in the last few years to the point that we can achieve experiences that are pretty much indistinguishable from the PC experience, at least on the tracking side, on a mobile device as we can on the big PC.
Right, on the tracking side, not necessarily on the display side.
The rendering side is still, I think, the mobile is still lagging behind what you can do on a big desktop PC. We don't use the GPU as much as like a big graphics engine does, and so you're seeing a lot of like low poly experiences and things like that in mobile VR and mobile mixed reality. And I think that'll continue for a little while because just the amount of compute available, and actually it becomes a thermal problem too. Like some of these processors are capable of delivering near PC experiences, but if you run them at that rate, the thing shuts down. Right. It starts to melt and you have a thermal issue. So those are the issues we're facing.
Do you see tracking as scalable? Is it scaled so that on an Android experience you're refreshing either slower or counting like a smaller area that you're detecting?
Yeah.
And how have you found that changes the experience overall? Is there a floor where you find 6DoF tracking needs this much compute, and are we there yet?
So, we look at different processors. We look at like Qualcomm processors. The Qualcomm 820 we think is sort of like just there in terms of being able to handle an experience that replicates what you saw here with Windows. The 835 is definitely there. The Apple latest processors like 810 is definitely there. there are trade-offs. You do need to maybe slow down your refresh rate and things like that. You have to trade off with the application. And the faster you update the map, the more stable your system can be, especially for users that are not trained in how to use a system like this. They'll just whip around real quick without really thinking about it. And that's one of the hardest things you can do to a system like this. And so it needs to update really fast when you're doing that, and you're really stressing the system. So we're not completely solved. I don't think anybody's completely solved it. Any of the AR SDKs that are out there, you can still break them. But it's exciting time to be working on this, and the resources, I think the compute resources are here today to pull it off. It's just, we probably need to iterate a little bit more on the actual software to make sure that it doesn't break in any cases. Or it breaks in a few enough cases. I mean, let's not forget that InsideOut systems also break in a bunch of different cases. Yeah. So the first base camp is, do we beat the InsideOut system? And then can we match the InsideOut system?
The outside-in system.
The outside-in system, sorry. Can we match the Lighthouse or the Oculus? And then, which I think in many ways we are. And then can we do things you can't even do with those systems, like let you run down a city street while tracking, or let you walk throughout your entire apartment while creating a model. So there's some interesting things we can do beyond that. But to answer your question, I think we're there, and I think in many ways the software works. It starts to depend on the application, and then people start to stress test it, and depending on how far you want to go in terms of the user being aware of how to use the system. Now I think the user needs to kind of know what they're doing, but next year they probably won't at all.
You guys must be as curious about ARKit as anybody. I would imagine that being on the horizon for iOS. What thoughts have you given to how ARKit can be augmented or amplified by having an external sensor? Is that going to be an area of interest to you guys?
Yeah, so we're looking at ARKit, and we're looking at ARCore as well, and we're looking at how we can bring some of our magic software experience to those tracking systems. They do some things really well. They tend to not fail in tracking, even if that means sometimes there's quite a lot of drift and other errors. But they're still really interesting in terms of targeting certain consumer experiences that weren't possible before. When you augment with new sensors like depth, you can eliminate some of the failure cases. You can eliminate some of the initialization. So if you try to use ARKit today, one of the first things you need to do for most experiences is point it at a plane and move around. And if you've got good lighting and great detail, that's really quick. And if you have bad lighting and the flat table like this, it can just completely fail. And adding something like active depth can make that process a lot easier. It's pretty similar to how when you guys tried this demo for the pure monocular version, we had to move a little bit to initialize it. And for the version with added sensors, you didn't have to.
Yeah. And we know that IMUs, one of the things that makes VR possible is the lowering price of IMUs. Do you see that happening for depth sensing cameras and IR cameras, or is that always going to be this premium level experience?
So I think it is happening. It's taking a little bit longer because to drop the price of each of these individual elements, like projectors and cameras, are actually pretty inexpensive, but you end up needing a bunch of elements. You've got to drive a laser, which means you need a laser and a laser emission system, which adds like a double cost. Then you need to have maybe more power, which maybe means a bigger battery. Then you need to have maybe 1 or 2 cameras that are infrared, high resolution. That's one cost, and now you need to process all that data, and that's another power consumption cost. So it's this snowball effect when you start to add these parts, and then you have to deal with all this more data and everything, and all those things add up to the total cost. So the individual parts are actually pretty cost effective at this point. They're not too far out of whack with what people pay for cameras that are on your smartphone today, frankly. It's just that there's so many parts. And so I do see that dropping over time, but the interesting trade-off is that the software side is able to achieve so much with less, which is actually a hindrance to the cost dropping on these more advanced systems, because maybe you don't need them. Maybe you don't need to add them to your BOM, and so maybe we don't need to get the price of that whole package down to $5. And so I think it's slowing the curve of adoption for those technologies a little bit, but with the explosion in apps that I think we're going to see over the next couple of years, consumers will start to get a taste for it, and then they'll start to say, I want it to be a little bit faster, a little bit better, and they'll finally be willing to maybe pay a little bit more for a device, or OEMs will be willing to take the plunge and deploy this across hundreds of millions of devices and not 5 million devices.
Or a little more convenient than setting up cameras all over your house.
Yeah, for integrated headsets, this is the way we need to go. Yeah.
All right, Jeremy, what did you think?
Well, it's interesting because it's basically like, this is what it would be like if the Vive had inside-out tracking. There it is. And it's very cool to see live, real-time world scanning. I mean, that's sort of, as we talked about with their other device, the Bridge, that doesn't do. This does that. And
Real-time.
so as we're moving towards a wireless VR or augmented reality world, that's what you're going to want. That's what you're going to need. And,
no, totally.
and experiencing that is really, really kind of exciting.
And the demo that we got was in 2 phases. I mean, they were really, it was really important to note that while we had, it was a Vive headset with a modified attachment on the front, this was their structural core sensor, there were lighthouses set up in the room to track the Vive controllers. They blocked the Vive lighthouses as we were using the demo. So we could prove it wasn't just using the lighthouses on the headset.
Right.
But the first demo was using just the binocular single camera inside-out tracking.
And you got capture of this so people can see what that looks like? Basically, it turns the world into it's like a neon Tron kind of aesthetic, where the edges of everything, there's a point cloud that gets created for everything, and then the software creates lines between points that make sense. So you start to see the outline of even mouse pads.
The outline, I think, was their secret sauce. That you can do point clouds, and I guess you find a balance between how much computation you want to put into the processor, how fast your refresh rate is, because you're locked into that for the camera. But I was able to navigate. I almost felt like it was like being like Daredevil. Like the world was black, but I was getting this like extra sensory perception where I knew the edge of the table was right here. I knew there was a computer monitor right there. I couldn't see what was on the screen.
Right.
And I couldn't see people's faces necessarily, but if people were sitting still enough, the point cloud around the person would eventually form.
Not into lines, because there's no straight lines.
But I could see the edge of tables. I could navigate around the world.
And I remember you reaching out and you were saying, yes, this is the TV, this is the desk, this is the mouse pad.
And I moved the mouse pad.
And it would stay until the system started to realize that you had moved it.
Yes. Yeah. So I think it trusts the world in terms of like knowing most things are going to be static. Your furniture, your boundaries are going to be static. So they're balancing the refresh rate that way.
Right. We still don't have a cap protection solution yet.
No, I don't think so. But that was a monocular system, and it was real time enough that it worked as a positional tracking system.
Absolutely.
Now, once you flipped on the actual the structural core depth sensing cameras and basically use it instead of Lighthouse, and you had to use this in a VR game, how did you feel that compared to a Lighthouse-based tracking system?
Well, the tracking, I would say, between those two experiences was very, very similar. I mean, compared to the Bridge solution, the frame rate's fantastic. I mean, it really feels top-notch. There's maybe a few extra milliseconds of latency. I was doing a lot of checking, like moving my head very quickly. And compared to the Vive Lighthouse sensors, there's maybe a little bit of some lag, some latency. However, obviously, this is like a very early rough developer kit. I could see inside-out tracking being flawless once it reaches consumers. So I'm not too worried about that.
It really depends on the content you're using. If the content really is very casual, watching a movie, very slow positional movement, more rotational based, because the IMU is going to be good enough for that, it's going to be totally sufficient.
My concern is always about motion sickness. Like I'm always concerned that people are going to be turned off. This is the first thing they ever try, and maybe they don't even realize it, but they get a sense of nausea based on just a few extra milliseconds of latency. So that's always a concern. But it's, I'm sure going forward this isn't going to be a problem. But what's more important is that, they were able to map a virtual reality and do positional tracking using this inside-out solution. And it worked extremely well.
And what was interesting to me was that Jeff kept talking about the mobile applications. While this was a desktop demo, really they're optimizing their algorithms, their computer vision, so that this can work on a high-end smartphone going forward. Because that's where the mass market adoption of whether AR or VR is going to be, is possibly going to be in the mobile headsets.
Well, with ARKit about to come out from Apple with the latest iOS, probably in a week or two, and AR Core on Android, I think we're going to start to see some real movement. If not with headsets, at least with just AR being a part of the vernacular and developers having a chance to develop things. Eventually, we all think and hope that this is headed towards wearables. And yeah, you're absolutely right. They said they have their inside-out tracking solution working on Android already. I mean, it seems like a no-brainer that InsideOut is part of the next generation, if not very, very soon, about AR as well as VR.
And I think being one component of a tracking solution, I don't think we're going to very soon find ourselves in a case where InsideOut's going to replace outside in completely.
Right.
I think some type of fusion is going to be essential if you want even track controllers. Like you asked, how are you going to track your 6 degree of freedom controllers with just one camera looking out?
I'm very concerned about that. I mean, the pitch from developers and, well, probably companies more than developers, is that as long as it's tracked by your headset when you see the device, that's enough, and it's not.
It's not for you.
It's just not, because in social VR or in certain games, there's always going to be the reason for you to be tracked when you're not looking at something.
Unless you put cameras on the controllers themselves or more cameras on the headsets to get a wider field of view for the computer vision, that's not going to be a solved problem.
Right.
I would love to see some type of sensor fusion where I'm using the high precision, high accuracy, high reliability of an outside-in system or even like the Lighthouse system combined with computer vision advances, so I get more dynamic chaperone systems and more dynamic ways of awareness of the world. I think some type of combination is in the future. It's optimistic.
I don't know. As long as there's a combination, we're always going to be restricted to a limited amount of tracked space.
You want to say, cut the cord.
Don't you?
Let's go wireless. Let's go inside out.
That is the dream. I mean, that is the dream, to wear sunglasses and go out into the world and have your augmented reality be a part of life.
Well, if this monocular system that we demoed is any indication, then we are going to be on our way there. And I am optimistic. So that's it for this week on Projections. We'll be back next week with more software, VR, AR talk. But thanks for watching. Subscribe to our channel, and Jeremy and I will see you next time.